Antes de comenzar, ¿alguno de ustedes tiene problemas con que yo la presentación en inglés? ¿No? Que pueda dar la presentación en inglés porque vamos a tenerlo más o menos igual. So, good morning. I'd like to thank you all for your time. My name is Jose Maldonado. I'm currently an undergraduate senior at the Polytechnic University of Puerto Rico. This is my capstone project I'm doing with my partner, Alexander Pellicier. My mentors are Carlos Alvarado, Joe Moncayo, and Adrimensores, as previously mentioned. So today we're going to be talking about the enhancement of modeling capabilities of a full flight simulator, and I'm going to get into that in just a second. First off, we're going to talk about what is a flight simulator. Okay, so a flight simulator is a device that allows us to recreate the flight of various aircraft and the flight environment itself. When I say flight environment, I mean that includes weather, air quality, turbulence, no turbulence, time of day, everything, so we can make the experience as close to the real thing as possible. So, basically what we're going to measure is how the aircraft flies, its handling characteristics. Is it stable, unstable? Is it agile, slower? What is its takeoff speed? Things like that. Okay, the second thing we're going to measure is how it reacts to control inputs. Control inputs being what the pilot puts in the joystick or in the rudder pedals or in the throttle. And to measure how that is going to affect the performance of the aircraft. Because you don't want an aircraft that is too sensitive on the joystick, thereby a pilot accidentally causing a small movement, making a big reaction from the aircraft. What are the uses of such devices? Well, okay, these devices are primarily used in flight training, design and development of the aircraft, and research into its flight characteristics. Okay, so the three are divided, the three are basically, flight training would be, if you're a commercial pilot for an airline, flying a airliner would be a cost of approximately $50,000 per hour of flight. So since a company can't afford to stop making profits from an aircraft and put you to go test yourself, they use simulators. The same thing with the Air Force. To give you an example, the F-22 costs $17,000 an hour to operate without weapons. The design and development, during the design phases, they create very specific simulators in order to test the aircraft before it flies, all the aircraft systems and how they're interacting, just to make sure that none of the systems coincide with each other. This is mostly done at a computer level. Okay, and the last is research into its flight characteristics. You pre-program different flight maneuvers into the simulation itself, and from there you measure what's happening. Is the oscillations damped? Are they not damped? Are they resonating? What's going on with it? Okay, so now I'm going to talk to you about the categories of flight simulators. There are more or less 7 categories, but I'm going to talk to you about the 2 most important ones because the categories can go from PC-based simulators that you can buy off the shelf, which wouldn't be that useful to us right now in terms of training and what we're trying to do for research. So the first one is the flight training device. The flight training devices you can find in a lot of universities that have flight programs, such as Interamericana. Those are fixed. You basically sit in a cockpit in a room, and they can be generic or they can be aircraft specific. Basically, when I say generic, it can be just a standard airplane model that they use with certain characteristics. If you're flying a general aviation aircraft, it'll be more or less within this range. Commercial, same thing. They all have a certain range. Or aircraft specific, meaning I'm going to fly the Cessna 172 SP, right down to that airplane. The flight systems and the environmental models are generic also. When that is basically, you have all your instruments, altimeter, you have airspeed indicators, you have all these different things, but they're just the same ones that every airplane has. It's not specific to that aircraft itself. And a low quality visual system is required, meaning that you have the ground, you have the sky, but you really don't have anything else. You don't have any geography or anything. It's just for the purpose of making sure it works. The one that we're going to be dealing with is called a full flight simulator. So all the aircraft systems must be simulated. Everything in it. How the throttle is arranged, how everything is put in the cockpit, must be recreated. the complete aerodynamic model is required. So if you want to simulate a Learjet, you better have the aerodynamic model with a high level of accuracy. The level of accuracy that we're looking at is generally around 96% close to the real thing. And outside world visual systems are required. That means we recreate topography, mountains, valleys, everything, so you can practice landing in any airport in the world or taking off. And a full motion platform is required. So you know that an airplane has 6 degrees of freedom. You can translate yourself on all 3 axes, and you can also rotate on all 3 axes. So that would be 3, 6. All right. You guys with me so far? Okay. So the general outline for what this project consists of. We're integrating various modeling and simulation technologies, which I'll get into further along, to create an alternative for flight testing, as in the recent years it's become extremely expensive and prohibitive. So the initial stage is we're going to connect 2 computers and create a network between them, and one is going to have MATLAB Simulink, which is a program that is commonly used in engineering, and the other is going to have X-Plane, which is our most popular simulation program for anywhere from enthusiast all the way to a professional level, depending on which quality you want from it. And the final stage would be to install that software that we've created into the Moto 622i full flight simulator, which is in the Polytechnic University, and our goal is to model any fixed-wing aircraft, even if it does not exist yet. That way you can test out a design before you actually have to go out and make a model of it. So, fixed-wing aircraft, by the way, is airplanes, as the wings are in the same place. Rotary wing aircraft would be a helicopter, so the wings are rotating. Okay. So our objectives, like I mentioned, are to model any kind of aircraft. Well, fixed wing, sorry. To predict aircraft prototype flight characteristics, so that way we can use it as an alternative for flight tests. To gather flight data from the simulation in order to refine every design that we are making and optimize it. And to adjust the flight parameters so we can test it under various conditions, say heavy turbulence or calm air. Alright, so why would this project be important? You know, how we justify doing this? Well, we want to create, not just for the industry, you know, for the newly emerging aerospace engineering department in the university. We're giving students a tool so they can understand the architecture of aircraft simulation, so they can learn about flight dynamics, control systems, and various other aspects that are embedded within that. The other is to generate flight data so they can analyze their own designs and see how they need to refine it. So that way our students, future students, will have practical knowledge. They have hands-on experience, not just having read it from a textbook. And the other side of it is to provide an alternative due to the recent rise in cost of flight testing. That has to do a lot with fuels and accessibility to materials. So the average prototype airplane costs about $100 million, just one airplane. A simulator can cost you about $250,000, a reconfigurable. The U.S. Air Force has reported cost effectiveness in using simulators of about 1 to 40 compared to flight testing. So here's just an example, a general example of different flight test programs that have been in the armed forces with their duration in months. So the longest one right now is a B-2 bomber, the big black flying wing that you see. That one lasted 96 months or 8 years of testing. In terms of total with design, development, and testing, it was a 20-year project that cost about, every aircraft, it's $2.8 billion, every one of those flying wings. Another example that you have, the latest one that they have is the F-22, was about 7 years. 6 years, I'm sorry. And every one of those, every F-22 cost $225 million to produce. Here you have the average flight test cost that the Air Force reported for the year 2001. I'm sorry I don't have any more recent data, but it's currently classified. And the scale of all these is in millions of dollars. So in non-recurring development alone, we have $2.6 billion that was spent. Those are just gone. Yeah, that's not going to happen again. In flight tests, we have about $37.8 million. I mean, wind tunnel tests. And just for suborbital flights, we don't even get those into like a satellite, we have $160 million. That's how much it usually costs. All these costs can be mitigated. Well, most of them, at least the flight test ones, the static and these, we can't simulate those yet. All those can be currently mitigated, and we can reduce the cost using simulation. So this is the simulator that we currently have at the university. It's the Moza 622i. It's currently the most advanced simulator you have in the Caribbean. It's full motion. And so first off, we have the cockpit, which is in here. You're going to have your pilot and your co-pilot sitting in there. It has about a 180-degree field of view, and you can recreate the cockpit instruments very, very precisely. It also has feedback into the control inputs. So it's not like when you're playing with your Xbox or with your joystick that you just put the joystick and you don't have any force going back into it. It reacts just like an aircraft would. It'll push back against you depending on the force and the velocity of the aircraft. Okay. Afterwards, we have what's called the Steward platform. This is a special type of platform that's used in these situations, and it also has a lot of other applications in the automotive and aerospace industry. But right now, what I want to focus on is it gives you the illusion that you are moving within the 6 degrees of freedom using a technique called acceleration on cueing. So I don't know if you know this, but inside your inner ear, you have 3 discs that have fluids in them. And that's how you balance yourself. Depending on the movement of those fluids, your body interprets it, and you know where your horizon is, or if you're accelerating, decelerating, or whatever you're doing. This machine is designed to trick you into thinking that you're moving. Since you don't have any reference to the outside world, your reference is what you see through the computers. So when you accelerate the aircraft, it kind of leans back as if you were getting pressed against your chair. And it creates that illusion. So you can mimic disorientation for pilots in what's called instrument conditions, which is a very low visibility condition. You can pretty much recreate every aspect with this type of simulator. The other part is the instructor's operating station. There's a computer there. You can't see it right now because it's at an angle. But the purpose of that computer is we alter everything there. We can tell the airplane that it has engine failure, that it ran out of fuel, that it's leaking fuel, that the electrical system's not working, that the radios are malfunctioning, or that they're setting themselves to the wrong frequency. We can make anything go wrong with the airplane in there. Well, wrong. Not happening in real life. And the last thing, that tower we have there, is the computer. There's 8 CPUs in that computer. 6 of them are just for processing all the data coming in. One of them is to do the rendering in the 4 projectors that we have in there. And the last one is to make the movements within the Stenson, the Steward platform, sorry. Okay. One very important thing is that, like I told you, this is currently the most advanced one that we have. It's also, the best thing about it that we have is that it is reconfigurable. Right now it has what's called an FAA, Full Flight Simulator, Level C rating. The highest is the Level D. But for a Level D, you need to be specific to that airplane. So it has to be the Boeing 737-200. It has to be that specific. And that would not be useful for our purpose of actually giving students a tool or being able to do research for aircraft design, because we need it to be able to reconfigure it. So this is a view of the cockpit. This is one of our friends from the university. So here you have the instrument panel, and you see you have a complete field of view. It goes all the way to the side here, and there's a seat here. This was taken from the co-pilot seat. This panel, you can remove it, and you can change it depending on the aircraft and how you design the cockpit. You can remove the control systems down here. You can change this into a joystick. We can reconfigure the cockpit completely into whatever we need it to do. It also has safety features. You know, it has here, this red button is an emergency stop button in case the person becomes disoriented or doesn't feel comfortable with what's going on. You just hit that button, the simulation stops, and it goes back down. The instructor also has a fail-safe mechanism. And this is what I was talking to you about. There are some servo motors within there that'll push back on you depending on the movement that you're making, thereby giving you a feedback into how much you're trying to move the elevator or the aileron. And these would be the throttle controls and propeller controls, or jet, because we can actually model jets too, and we just remove that instrument and we put in the one for jets. So it can be a single engine, multi-engine, we can do whatever we want with it. And say we want to model an aircraft that it wasn't designed to, we can just download the model and buy the parts from the manufacturer that would simulate that cockpit. Actually, the FAA, which is the Federal Aviation Administration, allows pilots that out of the 40 hours that they need for their private pilot's license, they can do 20 of them in here. And it's real enough that they actually count those 20 hours towards your license. So you could save money flying one of these. Alright, so I'm going to talk to you about MATLAB Simulink, which is a program running within MATLAB. It's a block diagram environment which helps us in making models and simulating. Most of you must be familiar with that program. It's very nice because you don't have to write the code. You just actually put the blocks in, establish the parameters, and it'll write the code for itself right there. So it supports systems level design. We can make various programs and make those programs run inside a bigger program. And we can just use those to simulate subsystems within a system. And it allows us to pretty much verify any mistakes that we're making before we bring it up to full scale. Alright, so the simulation software that we're using, like I previously mentioned, is X-Plane. X-Plane is an engineering tool because it's very, very realistic. And the physics engine is just great. And it can model fixed wing, it can model rotary wing. Actually, you can fly blimps in there too. You can model pretty much any type of aircraft, and you can. There are various versions of it, from the very basic version that you have just the airports in the U.S. to the global version. You have every airport in the world modeled there. And there's a commercial version which has a better physics engine, and that is the one that we currently have installed in the simulator itself. Alright, so it's also a great tool for pilots to keep their currency. The FAA has a requirement that every 90 days a pilot must fly at least 3 landings and 3 takeoffs. So if they don't have access to it, say you live in Iceland and the weather's too bad, you can actually do the currency with the simulator. That way commercial pilots can keep themselves current and not lose their certification. Okay, and also it is a great tool for us to predict how airplanes fly, as the level of realism, as we said previously, is up to 96%. What I mean by 96% before I continue is that there's a 4% difference in measurements between what you see in the simulator and what you measure in an actual aircraft doing the same maneuvers. Okay, so how we're doing this is we're developing plugin files. Plugin files are basically, you have MATLAB, you have X-Plane, and the plugins are what help one program communicate with the other one. Think of it as a translator just to make sure they're both on the same page. After we use those plugins, we develop them, we use them to create a network between those two computers, so that way they start interacting with one another. And after, with that network, we design an interface so that it's easier for the person to handle. That's why we're using MATLAB that has a block diagram, so you don't have to go and rewrite codes. You just go into the blocks themselves and you readjust the parameters. Because it's quite a big matrix that we're using for the data of the aircraft. It's about 16 by 9, so you don't have to go looking for every individual aspect of it. You put the data through the interface, make it a lot more user-friendly. And once the interface is complete, we'll be able to add different types of parameters. We can simulate different flight conditions, weather, air quality, like I mentioned before, or where the aircraft is itself. Say we wanted to simulate a rocket launch, we can actually simulate a rocket launch all the way up to the upper atmosphere. It allows us to do that. And model different types of fixed-wing aircraft, like I mentioned. Okay, so like I mentioned, we have the initial objective and the final objective. The reason for this is that we don't want to upload it directly into the simulator since it has movement. And it's a very expensive piece of equipment that we don't want to damage. And say the codes were faulty and it interprets the data wrong and it moves the cockpit really abruptly, we could accidentally injure a person inside the cockpit or a person outside of it, and we could possibly break a piece of equipment that's worth $250,000. So the initial objective, like I mentioned, you have first some pilot input, So that would be what the person is doing in the joystick itself and the controls. That signal goes into the computer that has MATLAB with Simulink, which would be what we call the flight parameter computer. Now, that computer sends the data through a network, whether it be through Wi-Fi, LAN, or USB, and it connects it to X-Plane, which would be sort of its output, which would enable the pilot to see what he's doing. So in a way, that would be sort of a feedback, because that would tell the pilot what to do next. Now, once we take it to the final objective, we're again going to have the pilot's input, which goes into the flight parameter computer again. But now this computer, instead of being connected to the one PC, is connected to a cluster of 8, which is the cluster that you saw in the simulator, the big black box. Now from there, you have the output that goes right there into the cockpit itself, which is also where the input would be. There you have a small view of the cockpit from above. All right, so this is a simulation startup procedure, what you have to do every time you want to do it. So first you're going to have to open up MATLAB and set up the file path, which is a little bar at the top. You're going to make sure it's in the file that you put in for the simulations. You're going to have to click on the shortcut for Learjet 24. Currently we're doing that one as we're still doing the research to make it feasible for any aircraft. So we're using a model that we already know works. And you're going to click on that shortcut, the MATLAB shortcut, so it'll open up the Simulink file. Once you have that, you're going to select cruise on for the flight conditions. That way all parameters are within the known range. And you're going to start the simulation and verify that they're synchronized, that the control inputs that you're giving are the ones that the aircraft is reacting to. Because if you're moving the joystick forward and backward and what's reacting is the throttle, we need to make sure we readjust the input channels before we continue with the flight test so we can get the correct data. And then you're just going to perform the different flight conditions using a joystick. There are 4 different flight maneuvers that you do in aircraft testing. They're universal for every aircraft. They're there to determine the stability of the aircraft and its handling qualities. So I'm going to discuss those now. First we have what's called the phugoid and the short period. So they're the same maneuver. They're an oscillation that is up and down. You can see the aircraft doing sort of a wave motion. Now the difference between them is that the short period has a period of 10 seconds. So from here to here, it's going to be only in 10 seconds, so the pilot has to give a lot more input into it. And the second mode, which is the phugoid, is a 100-second period. Basically, you're going to give an input upward, and then you're going to let the aircraft stabilize itself. Because as it goes up, it loses speed, therefore it has less lift. And then it's going to just start going down to compensate for that and pick up more speed. And then it generates too much speed and it goes up again, and it's a damped oscillation. Eventually it stables out. That's why it has a period of about 100 seconds. The magnitude of the deflection of the elevators is only 3 degrees. And the sample frequency that we're going to need is 100 hertz. So we have enough data points, which would be 10,000 data points for the simulation, to make it a viable experiment. So another maneuver that we have is the Dutch roll. Here you can see it from the front. It's a double combination. You're going to use the elevators and the rudder. Since it's a front view, it's kind of hard to explain it with just a picture, but you hit the rudder, which would make the aircraft sort of tilt sideways like this, and one wing starts going faster than the other, therefore it generates more lift. And once it generates more lift, it also generates more drag, which is called induced drag. It's drag caused due to lift. Once that happens, it's going to try to stable out, so it turns the other way. And now this wing is generating too much lift, and it just starts oscillating again in a damped motion till it goes to its original undisturbed state. So also we're going to have a sample frequency of 100 hertz and a time for the simulation of 100 seconds, just to keep the same number of data points as the other ones. So the last maneuver that we have is called a spiral, which is what you generally see in the cartoons as the airplane crashes. So we're going to get what's called a pulse rudder input, meaning it's not a gradual input. You're going to step on the rudder all the way in, very suddenly and very abruptly. with a duration of 5 seconds. What that is going to cause is the wing that's inside of the turn is going to dip, and it's going to start losing altitude because the lift vector is sideways now, so it'll start dropping, sort of like this. And also, the magnitude is also 3 degrees, because we use that to keep the deflection on the surfaces the same on every one, so we have control over the variables. And you're going to see the airplane start to go down, and you want to see how it stabilizes itself as it does that. So again, we're going to have a sample frequency of 100 hertz and a sample time of 100 seconds to maintain, again, the same number of data points as the other experiments. Basically, these 4 maneuvers, what are determining is how stable is the aircraft, meaning if I get it out of its normal range, how will it correct itself? For example, if you do that to a fighter jet, you just tilt it sideways, it'll go that way and it'll just continue till it crashes. If you do that to an airliner, it'll go unstable and then it'll straighten itself up and it'll fly by itself. Its own aerodynamic qualities make the aircraft more or less stable. Alright, so in conclusion, so once this research is finished, which would be by November, it will enhance the aerospace engineering program that we have at the Polytechnic University, and it'll help us support education in flight dynamics, control systems, aerodynamics, and aircraft design, which are 4 of the very core courses that we have for that program. And it'll also provide small companies which are currently developing in the island, such as Infotech, to have a flight test bed that they can use without actually having to invest in their own equipment. And that way they can test various aircraft designs. Alright, so any questions that you have?
Ok. ¿Está el simulador existente?
Sí.
Y ustedes van a hacerlo mejor. Eso es un ejemplo.
Sí, ahora mismo la forma que funciona es que tú quieres usarlo y tú quieres probar el avión, pues tú tienes que hacer un modelo aerodinámico de cada uno, entonces instalarlo y después volarlo. Pero todas las ecuaciones que gobiernan la estabilidad del avión y sus características de vuelo son universales. Lo que cambian son los coeficientes que hay en la ecuación, ¿verdad? Y esos coeficientes uno los va sacando con varios cálculos. Pues lo que queremos crear es un programa que tú vas haciendo un input de los parámetros de ese avión, cuán lejos está el elevador del centro de gravedad, cuánto es su área y todas esas cosas. Y según tú vas poniendo esa data, eso se va poniendo en la matriz. Y el sistema de control se va ajustando según tú pones esos parámetros para que entonces ya ese modelo aerodinámico se va haciendo según tú le das la data.
¿Y en qué etapa estás ahora con eso?
Ahora mismo te puedo hacer una pequeña demostración. Ahí tenemos un ejemplo. Esto es Simulink. Y aquí tenemos con nuestro controlador y tenemos todos los outputs de los diferentes controles, alerón, rudder, throttle y el elevador, que van hacia esto que se llama el Explain Communicator, que estamos diciendo, para simplemente nosotros poder tener consistencia ahí. Pero esto es un output que manda la señal. Ahora mismo, como es dentro de la misma computadora, es un User Datagram Protocol, que es un UDP Connection, que es una conexión que es vieja, que existe desde el 80 para Internet. Y cuando él envía esta señal, aquí tenemos un display también para saber cuál es nuestro output en grado y el tiempo. Acá nosotros podemos poner cuánto es el tiempo de simulación que va a estar durando. Y esto simplemente es para que no haya, el programa no nos lea que hay outputs desconectados. Pero estos outputs ya no se necesitan, los únicos que se necesitan son estos dos ángulos, que es el ángulo de pitch y el ángulo de roll. Ok, ¿puedes darle? Nosotros, este es el programa de simulación. Ahora mismo la calidad de video no se ve tan alta, pero puedes ver que reproduce todos los sistemas dentro de la cabina. Esto es que tenemos ahora mismo, un jet que había de concepto de una compañía que se llama Cyrus. Entonces, pues aquí tienes todo, porque se supone que es un jet futurístico para las personas, era privado. Y cuando nosotros queremos correr la simulación, ¿les puedo enseñarle los plugins, por favor? Ok, le damos aquí a los plugins y tenemos el folder que habíamos hecho, ¿ves? Advanced UDP Simulator, y le das Start UDP, lo que le dije, el User Datagram Protocol. la comunicación con Simulink. Cuando tú le das eso, el programa se frisa por completo, porque él está esperando el input que le vamos a dar de Simulink. So, cuando él hace eso, usualmente no responde porque necesitamos las 8 computadoras para que pueda procesar esa data. Nosotros volvemos aquí y le damos play a la simulación y él empieza a hacer el sample time. Ya mismo lo vas a ver aquí y ya el simulador está funcionando, porque ahora el input proviene de máquina. Nosotros podemos usar, ahora mismo teníamos conectado un joystick, ahí está acelerando. No tenemos un controlador conectado, solo podemos hacer muchas maniobras de vuelo en estos momentos. Pero uno puede empezar el vuelo, uno le dice al simulador, pues estamos a 10.000 pies de altura, la velocidad es 450 nudos, que es más o menos una velocidad promedio para un jet. Y ahí empezamos. Sí, el piloto parece que está borracho. Y por ahí vamos. Y como puedes ver, hacía calor, el avión tenía que hacer. Pero ahí está, Alex, no lo pongas en correr, solamente dale la vista a la fuerza, por favor. Como puedes ver, el simulador, ok, el avión, cuando nosotros hacemos los renderings, tiene todo lo que tú te imaginas. Puedes ver que adentro están hasta los asientos, dónde está el piloto. Si nosotros quisiéramos probarlo lleno completo, nosotros podemos decirle que hay personas aquí, o sea, está lleno completo el avión, cuánta gasolina tiene y le ponemos maletas atrás y todo, para uno ver cómo cambia el centro de gravedad del avión según tú lo vuelas.
Y eso es algo adicional que ustedes están haciendo que el programa no lo tiene.
El programa tiene la capacidad de hacerlo, pero no lo está haciendo ahora mismo.
Okay.
Porque como tiene Physics Engine que lo había mencionado, él puede hacer todos esos cálculos, pero tú tienes que especificarle qué es lo que está ocurriendo. Porque si tú lo dejas en los settings que tiene ahora, pues él asume que tiene gasolina infinita, sobre el peso nunca cambia, hay una persona nada más. Ajá. Nosotros tenemos que ir diciéndole cuáles son los parámetros.
O sea que si tú dices que antes estábamos, o el simulador es más o menos un 96%, tú lo estás llevando casi a 100%.
Eso es lo que queremos hacer, llevarlo casi al 100%, okay. Porque, como le mencionamos, un prototipo puede costarte hasta $100 millones. Bueno, más o menos ese es el precio promedio. Hay prototipos que cuestan mucho más. Y, por ejemplo, ahora mismo que está creciendo la industria aeroespacial en Puerto Rico, las compañías no son suficientemente grandes para poder pagar algo así. Aunque tenemos acceso a la base Remy y la base de Ceiba, que la base de Remy era un Shuttle Alternate Landing Site, así de grande de la pista. Y tenemos un clima buenísimo, de los 365, 350 días son flyable. Pues no tenemos el prototipo todavía, entonces ellos no pueden estar haciendo varios prototipos según van refinando el diseño. Porque, por ejemplo, el F-22 hubo un prototipo. Ese prototipo se determinó que era muy inestable. Se hizo otro con otras características aerodinámicas y otro programa que estaba controlándolo, porque esos aviones son demasiado...
Sí, durante los 7 años antes de salir al mercado,
sí,
fue todo ese proceso.
Sí, y como quiera, después cuando sacaron el diseño, usaron un simulador de hecho para determinar qué era lo que estaba ocurriendo mal con el avión, porque estaba teniendo unos fallos. Por ejemplo, en el Air Show del 2011, en Lakeland, Florida, hubo un F-22 que estaba despegando y cuando estaba haciendo su steep climb subiendo, se apagaron los 2 motores porque la computadora los tumbó.
¿Eso fue en el simulador?
No, eso fue en vida real. Y usaron el simulador para arreglar ese problema.
Okay.
Y entonces determinaron que era que la computadora estaba detectando un parámetro fuera de sitio dentro del compresor de la turbina y como failsafe se tumbaba. Pero ahí tienen un fallo del avión más nuevo del Air Force frente a 40.000 espectadores. Y después lo tuvieron que sacar de la pista con carros de golf y tractores. Sí.
Y si yo te pregunto del 1 al 10, ¿en dónde está ahora mismo tu...?
Ahora mismo,
no estás con tu...
Hasta noviembre, ¿verdad?
Sí, tenemos hasta noviembre, vamos como por el 40%, yo diría.
Un 40%.
Sí. Porque todavía falta poder... Ya habla una computadora sola dentro del mismo, ya puede hablar de una computadora a otra, lo probamos con una conexión de Wi-Fi y estaban comunicándose lo más bien. Ahora es ver cómo podemos usar MATLAB para que haga ese sistema que funcione más universal. El problema que estamos teniendo es que los sistemas de controles que hemos podido hacer hasta ahora funcionan para ese jet en específico o el Learjet 24.
O sea que el proyecto es para ese jet específico.
Ahora mismo estamos usando ese porque es el que sabemos hacer.
Okay.
Pero la meta es hacerlo para que funcione con todos. Es que ahora mismo, simplemente para poder probar la comunicación, pues
estamos utilizando
este es el sistema de control que tenemos ahora mismo. Dale máximo. O por un poquito más chiquito. Este es el sistema de control que estamos usando para roll, los alerones. Cuán inclinado está de lado para ese avión en específico. Pues ese lo modelamos usando el libro de nosotros, Flight Dynamics, el de Modeling to Simulate, un libro de Francis Napolitano que va explicando cómo modelar aviones. Entonces el research de nuestro mentor, Moncayo, él ya había hecho muchos tipos de simulación así para hacer unmanned aerial vehicles, como los aviones militares nuevos que hay ahora, que el tipo está en Kansas volándolo, pero el avión está despegando del Irak y lo están controlando vía satélite. Pues están haciéndolo, él está haciendo unos que se vuelan solos. No hay ningún tipo de input del piloto. El avión vuela solo, si le pegan un tiro, él se diagnostica solo y él corrige su forma de volar para compensar por el daño que tiene. So, de ese research que él está haciendo es que estamos derivando los sistemas de control, porque son los sistemas de controles que se van adaptando según la situación. ¿Alguno de ustedes tiene una pregunta? ¿Quieren saber?
No, te felicito.
O sea que ustedes esperan llegar hasta un 100% que se
Nunca
asemeje.
no puede llegar porque sabes
Pero, sí.
que
Y cada por ciento ustedes se acerquen, pues ayuda y que si vale 100 millones en crear un avión, ustedes lo están haciendo
sí.
ahí.
Por eso lo que le había mencionado del Air Force, cuando está haciendo las pruebas, el cost effectiveness de ellos, cada dólar que gastan en simulador sería aproximadamente $40 que gastan en un avión de verdad.
Okay.
El punto técnicamente vamos a traer también un mercado directamente a Puerto Rico. O sea,
Sí.
si después que logramos este proyecto, más adelante pues, van a venir, seguir expandiendo el proyecto. Entonces pues, otras compañías quizás puedan venir. O sea, que,
Sí.
Entonces podemos mejorar el mercado en Puerto Rico.
Pueden invertir, pueden comprar otro equipo de
Sí,
esos.
se pueden comprar.
Sí,
se pueden
mejorar
comprar,
la industria.
No,
Una nueva industria totalmente en Puerto Rico.
porque está creciendo lo de aeroespacial, pero poco a poco. Pues acuérdate que ahora mismo pues tenemos la parte de data analysis, que es lo que hace la mayoría del tiempo Infotech. Pratt & Whitney tiene análisis de turbinas y de heat exchangers dentro de los aviones, y Hamilton Sundstrand pues ya se le terminó el contrato con NASA, pero antes aquí, ustedes saben los bultos de los astronautas que ellos tienen atrás, eso se producía en Santa Isabel. Pero ya pues como no está ahora mismo el programa de Space Shuttle y están usando las naves rusas, pues los suits que usan son rusos también.
¿Cuánto tuviste que costaba un minuto de vuelo del...
¿Un minuto?
Sí, del avión que mencionaste?
No, una hora de vuelo.
Una hora.
El F-22 cuesta $17,000 aproximadamente la hora de vuelo. Un F-18 cuesta $16,000 y... Y el costo por unidad de un F-22 es $224 millones. Dígame.
El programa solamente simula el vuelo, pero no simula todas las operaciones del avión en vuelo.
Sí.
Estamos trabajando en eso para que pueda asegurar todos los sistemas, desde el landing gear, cómo se abre, cierra, cómo los flaps se abren, los mecanismos, todo.
Y también
poderlo.
un evento virtual.
Sí, porque usted sabe que probar un avión pues es algo serio. El piloto de prueba está arriesgando su vida, básicamente. Estamos tratando de minimizar esos riesgos para las primeras rondas de vuelo. Porque, por ejemplo, ustedes se acuerdan con películas como The Right Stuff, que acá rato se estrellaban los aviones de prueba. Y era bastante común que la gente se muriera. Más o menos un 35% de los pilotos de prueba del Air Force murieron en los 50.
Pues muy bien. Pues le agradezco a todos los que vinieron. Gracias por sacarle su tiempo, y los que no habían estado aquí en el Colegio de Ingenieros, bienvenidos.
ya cuando se gradúen, o proyectos del año que viene, o cualquier otra actividad. Así que les estaremos avisando vía email, los contactaré, y creo que tenemos una que otra presentación más que no pudo venir hoy, que estamos verificando si la vamos